And now the main lecture will commence. So what were we talking about last time? Process-centric modeling, discrete event modeling, patient flow modeling. It goes by various names in different contexts. AnyLogic calls it network-based modeling, confusingly. It's a third major type of modeling that's quite distinct from that has a quite different perspective than the perspective associated with agent-based modeling or system dynamics modeling. Can anyone remind me of a few hallmarks or characteristic features or themes that are brought out in process-centric modeling that that we discussed last time? Yeah.
The model is from the perspective of entities who go through a workflow and consume resources.
Well put, Jason. Well put. The model is created sort of from the perspective of entities or sort of processing these entities who flow through these sort of flow charts that describe in a fairly declarative way the processes that operate on those entities and whose processing is itself contingent upon or dependent upon resources. And when there's a lack of resources, what happens? They wait, by and large. By and large, they wait. There's actually more flexibility associated with that. We can, for example, have agents balk at certain phases. So, for example, if they wait too long, they may decide to leave, to depart the system via a different path. And there's certain operators in AnyLogic. Unfortunately, this is not one of them, but in AnyLogic's libraries whereby there's extra connectors so that they could balk if they've waited too long. There's also capacity limits. So there's some limits to how many people, for example, might be waiting for a certain resource. For example, this procedure, there's a maximum capacity associated with that, and that dictates sort of the size, the maximum size of the queue that can be associated with that point in the process, and that imposes some limits. But I think Jason put it very, very well. Perspective of entities flow through delineated series of processes in which consume resources in order to make progress. Okay, so well put. That highlights a number of features of this sort of modeling, and I noted the presence of queues, processes, flowcharts, resource pools. So by and large, like the entities themselves, the resources are treated in a fairly anonymous way. In contrast to agent-based modeling, where heterogeneity is kind of the name of the game, and agents differ, perhaps in sex and income and ethnicity and all these different characteristics very routinely in the state that they're in and their location and their position and network. By and large here in discrete event modeling, we have more or less anonymous agents, and we have these pools of more or less interchangeable resources. These pools where there's a set of doctors, and it's viewed as kind of being an unnecessary detail as to which particular doctor you're assigned. There's a set of nurses, a set of staff, a set of scopes to work on you, a set of procedure rooms that you could be operating in, and it's seen as immaterial which particular one you're routed to. It's like catching a taxi. You don't care, when you go off and take a taxi you arrive in a city, you take a taxi to a certain location, and then you take a taxi back to the station at night to return home. you don't expect it to be the same taxi. It's from a taxi pool. It's from a pool of taxis. Yes.
So this might be getting into hybrid modeling stuff, but let's say in one of these healthcare models, I have a patient with particularly difficult and special needs who say needs extra time with the doctor or two doctors to complete a task, or like a bariatric patient needs several nurses to move them.
Right.
Is it possible to incorporate that sort of heterogeneity among patients in this type of model?
That's a good question. So the answer is yes. We could incorporate some measure of heterogeneity into this, and one common way to do that would be to do it at these branch points. So for example, one way to do it, well, it's leaving entities kind of more or less synonymous with, let's suppose it's a difference about that entity that only affects one point in the flow. That, there's a set of nurses required, to move this patient at one point. Then you could have a branch that sort of flips a coin and says, hey, is this patient an highly overweight patient? If so, we need this extra support needed here. Is this patient a particularly puzzling case? If so, we need to do this extra diagnostic imaging on them, right? But it requires somewhat more precision and somewhat more mechanism, I should say. If these are persistent characteristics of a patient that we want to capture. For example, capture the fact that this is a patient who's has issues with dementia, and that might materially impact many stages of the process, right? Or this is a patient, perhaps a patient who has bariatric issues would be a good example, because that might affect a lot of stages of the moving. So we don't want to just flip a coin every time. We want to say, oh, this patient is in this special pool, right? So there's many ways we could try to kind of handle that within the broader framework without too much extra mechanism. We could have a separate flow for those people. Once it's determined that they're bariatric patients, they flow through a separate process. So it splits once, and then from then on, it's remembered by being, oh, you're in that process, that flow progression rather than this one. But at some point, you might want to bite the bullet and say, well, let's give this entity some characteristic, right? Some property, some attribute that remembers this sort of thing. And we could do what's called subclassing, and we could create a class that derives its basic mechanisms from an entity, but it records some extra information. Maybe that information is just statistics on how long it's taken to go through the system till now. But maybe it's some persistent characteristics that will follow them at least through this encounter in this network, until they flow out, when they'll disappear. So we can do that, but now you're starting to talk about things that, as you indicated, are getting us closer to hybrid modeling. They're getting us closer to sort of the idea that the entity is in fact an agent. And it starts to depart from kind of the normal mechanisms. Another example where there's real tension is, let's suppose, the patients you've seen before, you want them to be seen by the same doctor they saw before, right? How do you do that? Well, now, not all doctors are interchangeable, not just one pool of doctors. Maybe we start to have to differentiate different pools of doctors that are more experienced and called in for serious cases. Doctors, maybe even distinguish individual doctors so that you can bind to that same doctor. And again, we're kind of getting into the tensions that push us outside the most archetypical uses of this sort of modeling. Okay, so we can accommodate a lot of that, but at some point you start to kind of force fit it, and it's actually easier to do a sort of hybrid models. Yeah.
Isn't that, I don't know if I haven't been paying attention fully, but isn't that sort of like the essence of this type of model, is that your resources are non-distinguishable from each other? Like from a pool of doctors, no doctor is distinguishable from the other, so you can't really encompass the idea that one person wants to see the same doctor over again?
So yes, what I'm saying is that that's sort of in accordance with the general philosophy that you have these. So Darius's question was, isn't kind of the main hallmark of this, or the kind of the characteristic of this sort of modeling, that we don't have to get down to the level of individual doctors? We're dealing with these pools of interchangeable resources. Yes, that's sort of in alignment with the philosophy and in alignment with the archetypical sort of the typical case that we look at. But as often is the case, when you have a type of modeling, sometimes there are, warts and little imperfections to your situation that means it doesn't fit in perfectly. And so you end up doing some things that push at the edges. Some things are completely straightforward. Like, I'm not going to say there's only one pool of doctors, because there may be, residents and attendings and medical students, and those are 3 different classes, and we put them in different pools. Or, you have very senior doctors who are highly experienced, and we distinguish them in a separate pool because they're called in a specific way for certain types of cases.
But yeah, the point is you have to put them in different resource pools.
Yes.
You can't distinguish
Correct.
members of it.
Correct. And in some ways it's like system dynamics modeling, where to remember that, these are male infectives versus female infectives. Can we do that? Yeah. How do we do that? We put them in separate stocks. We put them in separate stocks. And here we put, when we need to represent heterogeneity, in the same way, representing heterogeneity in system dynamics, we divide things into separate stocks. Heterogeneity that's static, like what sex are they? Heterogeneity that's dynamic, like what age they are. To distinguish that, we divide into separate stocks because stocks are well mixed. They're memberless, they're homogeneous. Similarly, for discrete event modeling, we have these pools. The pools are homogeneous. We draw from them, and that's some of the power of the technique, that we can represent this whole class of vials of vaccine, or partially assembled cars and their engines, and we can represent these broad classes of staff in a more or less interchangeable way. And you're right, that's a lot of the power of the method, and it affords us a very crisp description. If we need to distinguish these things, which we often will at some level, different levels of expertise or different levels of experience, because it bears on the number of mistakes made, the risk of mistakes, then we separate them into different pools. And then at some point that gets really awkward, right? At some point you start having one pool per doctor, because you want to say, I want that doctor because that's the one I saw last time. Or you want to remember, that's the same patient who was here yesterday because they didn't get good treatment yesterday. Now they got infected overnight and they're representing. Their pain wasn't cleared up, perhaps. And now we're sort of stretching at the boundaries of this, and hybrid modeling becomes very attractive. Is that helpful?
Yes.
Okay. Great questions. I welcome these. Any other sort of questions or concerns or interests here? So we talked about these set of features of this, and then we talked about this notion of some operators, and I'll just leap forward here, reminding people that entities are these sort of parties that flow through the system and around which the system is centered. It's centered to describe the processes operating on entities. The entities collect resources to them and are associated with resources as they flow through, but those operators that we look at are focused on describing things that happen to entities. Resources are needed, proceed for certain stages here. I'm looking at main phase 1 here, which is particularly bereft of rich resources. This would be a better example. So we have a network sees, for example, and we can have, for example, balking associated with this timeout here, coming out there, and we can have preemption, people coming in with higher priority or what have you. But here we have these operators, and these operators are operating upon entities. And you notice it says a list of resources that are required for seizing. Those are being seized and associated with this resource. They're being reserved by that resource. Oh, excuse me, by that entity. They're being associated with the entity, being reserved by that entity, these resources. These resources are needed for proceeding. And so if the resources aren't available, they wait here. They wait until the procedure room, the doctor, and the scope are all available. Okay? And we have these resource pools from whence those resources are drawn. These flowcharts, people flow through them. They're often nonlinear, as we talked about, and they can be hierarchical. And we have these operators we can draw from the palette to describe things largely declaratively in these flows. Okay, so I talked about a set of operators last time. Source operators. What are they? What's their function? Anyone? What's the function of a source operator? Its name should allow at least
to produce entities.
Produces entities. It produces these. It pumps out entities. Here we have the source, and the source indicates the rate at which entries arrive. We can actually specify it with a rate. We can specify it with an inter-arrival time or a rate schedule, and we can even ask it to be manual, that someone calls an inject method. We say inject an agent or an entity, and an entity comes about. Useful for hybrid modeling. But you notice here, for example, I specified a rate, and there's an arrival rate of 0.5. This is a memory-less process for each unit of time. There's a 0.5 chance per unit time of that agent arriving. So the average time between agent arrivals is. This is a rate, though. This is a rate of arrivals. This is their chance per unit time that a new entity will arrive. So what's the average time between arrivals of entities? It's 2. It's 1 over 0.5. It's the same few-ish sort of repetition of this concept. We saw it in system dynamics, first order delay. We saw it in agent-based modeling, rate-based transitions and state charts. We see it here. It's the same thing. Take the reciprocal, you get your average time between, average inter-arrival time. Sinks. Sinks destroy agents. Sinks are where agents disappear. They vaporize. They're not persistent elsewhere in the model. And this is a source. Sink here is where they disappear. Okay. Network enter and exit, that basically associates them with a network of resources and locations. Think of it as like they enter a ward, a specific ward of a hospital where a bunch of resources, and a network exit. They leave that. Maybe they go to a different ward. Select output, we can kind of branch which way we go, and we can have actually joins as well, joins of multiple paths, and then a delay that there's something that has to happen for a certain length of time. And you'll notice with this delay that we can specify the length of time. And of course, this being AnyLogic, it allows us to specify these snippets of Java code. So here's our uniform thing, and finally, so this one, it's a happy, I did Control J, and it showed me where that is in the code. But here, this delay time, we can draw this delay time from a distribution. So someone comes in here, what's their delay going to be? We draw it from this distribution. And here it's uniformly distributed as a continuous number between 0 and 10. We could specify any number of distributions, or we could specify an exact number, or we could even call off to a function which computes that, right? So we have these various operators. Those are particularly simple operators in the sense that they don't require, they're not contingent for progress upon resources. Okay, so now I'd like to get, though, to the more, slightly more subtle ones, which are talk about operators which depend on resources. and where if they're not available, people queue up and wait for that resource. Okay, we have two types of operators that I really want to emphasize. Some have to do with logical reservation of a resource for an entity. They have to do with the assignment of that resource to the entity. The entity may be one place, the resource may be another, but it's logically assigned. It's reserved by that entity, right? It's associated in a conceptual level with the entity, even though it may be physically distant as of yet. So you could have a room reserved for you in the library or in the health sciences library to meet. So here we have a seize, which reserves a resource, and a release, which releases that resource. Okay? So that's great. And I want to distinguish between that logical association, that logical reservation on the one hand, with the whole issue of, does that resource travel around with you? Are you physically co-located, and is that guaranteed on an ongoing basis? Okay, so if we look at this linear chart, which I think is associated with main phase 3, we'll find that the network seize operator, for example, specifies this set of resources that need to be reserved for this entity. We can specify them separately in a separate operator, but here it specifies all three together. So this seizes one resource from the prop room pool, from the doctor pool, and from the scope pool. And one resource may be seized while we're waiting another, which for those from computer science background may bring questions of deadlock into your mind. As long as you reserve them in the same order every time, we can avoid unnecessary risk of that. So here are the declarations of the pools that are reserved, and the network seizes one of these resources from each pool. And once it secures all of those resources, then it proceeds onwards. And it will go on to separate operators. So this entity is going to reserve all of these resources. Note that some of the resources remain as yet distant from this entity. This entity is actually reserving these from the distant confines of this waiting hall. They're actually reserving a procedure room, and that's fine. It's going to be reserved in their name. They will then, in the fullness of time, flow down here and move to the procedure room. Which procedure room? To which procedure room will they move at that point? To the one that's associated with them. It's entity-centric. When we move them later to that procedure room, we're going to be saying, move this entity to the proc room. And guess whose proc room that is? Guess which particular proc room? It's not just any random proc room. It's the proc room that's associated with the entity that's executing at this point in the process. So again, when I say it's kind of entity focused, what I mean is that these operators, when they'll say, for example, hey, move to this resource. I say, well, which one? Well, it's the one associated with the entity. They're focused on the entity. The entity is kind of the center of attention as they get operated upon by these processes. Does that make sense? Okay, so let's continue on our discussion here. So, seizing is reserving. Releasing, the opposite of that is releasing. That unreserves it. It dissociates it. It no longer is assigned to this entity. So here down the road, it releases all seized resources in this release thing. It says, hey, I'm done with those resources. I don't reserve them for me anymore. So we have this pair, network seize, and then the release down there. Okay. Yes.
So if I'm understanding it correctly, it sounds like you can bind an entity to a resource, and you can bind an entity to a physical location. In the sense, at least, that it right to think of it as, you know, a space, like a physical space, or should I be thinking of it as something else?
So I'll come back to this slide here. So it's a great question from Darius, and I will come back to this slide where I note that it's not two solitudes, that there's sort of physical spaces and then there's resources. Actually, AnyLogic supports several classes of resources. Okay, resources come in various forms, and AnyLogic distinguishes three types of resources. One, resources that are portable. What do you see? I'll go at the extreme. Resources that are mobile, that have agency. Give me an example of a mobile, a resource with agency.
Doctor?
A doctor, a nurse, a staff member of various sorts. One could think of others as well in various contexts, but those are some fine examples. Moving towards progressively less ease of movement, we have portable things. Portable things are carryable. They can be carried, but they can't move on their own. They have to be moved by an entity or by a mobile resource.
Okay.
And then we have fixed resources.
So that'd be a room.
And that'd be a room.
Okay.
A room or an MRI machine, which is also associated with the location. It's a fixed locational.
So in essence, there really only is two things in one of these types of models, either an entity or a resource, and then everything else is just how the entities interact with the resources.
At a certain level of abstraction, Darius has argued perhaps there's two types of fundamental things in these models. It boils down to entities and to resources. That those are the sort of nouns of discrete event modeling. At a logical level, I would cautiously say, sounds good to me. Nothing else is coming hugely to mind as sort of the missing piece. I mean, you could say, well, it's the flow chart that defines the progression, but in terms of the nouns, the flow chart is kind of about the verbs. The nouns, there's kind of resources and there's entities, and there's several types of resources. And the resources are textured in the sense that some can carry others and some are fixed, etc. But yeah, I think that's kind of a fair division.
Okay.
Yeah.
Quick follow-up question then. I can say that a entity is attached to a resource or a resource is attached to an entity. Is there any distinction between those? Or is it a bidirectional?
The logical reservation occurs, the resource is assigned to the entity. But that's a relational construct in the sense that you could, by extension, that means there's an entity associated with this particular resource. It's just our operators are defined here for, according to defined on the entity. And it's the entity that flows through this flow chart in this version of AnyLogic. Now, I will muddy the water a little bit and say in AnyLogic 7, which was just released, it has some substantive advances, and one of them is that resources are given more of a leg up in life. They're given more of treated more as first-class quantities in the sense that you could have kind of flows associated with resources. And so they can go through stages of preparation or what have you. And so that muddies the water a bit, but it comes down to the Clintonian dichotomy between entities and resources that you articulated so well.
Are you going to publish that?
So I would welcome a cooperation on this. on this matter. Yeah, it's a fine distinction. The distinction between nouns and this sort of model. Okay, other questions? These are great questions. I can see you trying to grapple with how does this type of modeling fit in with the others, and I've oft grappled with that very issue, and so it's a pleasure to see others sort of working with that. Okay, so we talked about network seized and network release. I'd like now to talk about network send to. Okay, now network send to is actually an operator that operates, and it's the next in our process here. It's an operator that operates on the resources associated with the entity. In that sense, it's entity specific. You notice it's saying like to move the doctor. Well, which doctor? It's the doctor associated with you. It's the entity. Okay, but it's the doctor who's actually doing the acting here. The doctor goes, and what do you think the doctor does here? Can anyone say? What is the doctor doing? Can anyone? Yeah, the doctor is actually moving to a scope, and the doctor, that scope has already been seized. Where has that scope been seized? Or should I say withered? It was seized and network seized. Remember, they all got seized together. Here, the prochrome, doctor, and scope, and now we're sending the doctor to go to the scope. Which scope? Which scope is it being sent to? Same entity. Yeah. So this is the doctor for the entity going and getting the scope reserved by that same entity to the seized resource unit. In which one? It's the associated scope. Okay. So the doctor is going to get the scope. Does that make sense? It requires kind of a different way of thinking about it, right? We're kind of describing this from the perspective of the entity. And okay, it's the doctor associated with the entity going and getting the scope associated with the entity. Not just any scope, that scope. Okay, so this is network send to. We're moving a resource to another resource associated with the entity. We could move it to the entity themselves. So we could move it to a specified node or some home of some resource unit, like a staff lounge or something. We have those options. In this case, it's going to a resource, okay? And we can actually move multiple resources together. So here's send to patient. What is this one doing? Can anyone guess? It's the same operator. Network send to. So it's sending a resource. Which resources is it sending? Yeah, the doctor and the scope. How is the scope moving? It's moving with the doctor. It's moving because the doctor is there to move it. Suppose that we omitted the doctor. Suppose we only were to say move scope. Well, you folks can do it if you want. You can frob it right now and you can run it. And what do you think will happen? It won't compute because that scope can't levitate over. It can't just move on its own agency. It needs the doctor to move with it, the good doctor. And so that allows the doctor to scope in to whither do they go? To the entity. They're going to the entity associated with them. They're going to the entity that has reserved them. That's associated with them. To which they've been assigned. And that entity is located at a distant point. That entity, in fact, is located over here in the waiting hall. So they're going to be moving over to that entity. Okay? They're logically already reserved by that entity, but they need to get to that entity. And then what do? Well, they're going to go and attach to that. They're actually going to bind to the entity. So when the entity, so this is different than Cs. They've been reserved by this entity for quite some time now, since that network Cs. But now they're actually going to be attached to the entity, meaning that if the entity does what? They will also, if the entity does X, they will also do X. Move. Okay? So they're going to be attaching, this is attaching the entity to all the non-static resources at the entity location. And guess which of those are? The doctor and the scope. Yeah, there it is.
Just trying to break the system a little bit here. Let's say, so I'm working out to a situation. I want to imagine what would happen if so the entity has allocated or received or whatever a certain resource.
Yeah.
Let's call that resource mobile, so it's going to move to that entity.
Okay.
It sounds like the send to patient action, if you will, is kind of it's a discrete thing. Like it happens and then it's done, and there isn't really sort of like a chance for interruption in the meantime. It seems like it's kind of just an action that gets executed and then it's completed.
Yeah.
It doesn't really pause in between. But I'm just trying to
okay.
get to the idea that is it possible if somehow the moving of the resource to the entity gets interrupted and the resource cannot make it to the entity, what will happen in that case? Will it just kind of be stuck in limbo? Will we get a seg fault? Will we, will it stay allocated, but it's just kind of continuously trying to call the send do function over and over?
Well, okay. So I was trying to segment this with a separation of concerns. I was trying to segment this lecture into two pieces. One talking about the logical functioning, and one talking about the visual representation and kind of the animation associated with it.
Am I jumping too far ahead?
And one thing you'll find is that actually the send to patient is not instantaneous. There's actually a movement that takes place on a path that they actually travel on, and in fact won't execute the next network attached until it's reached its destination furthest. But I think your question is a good one. What were to happen if suddenly that path were to be disrupted, right? If suddenly that path were to somehow get changed so it can no longer go to the destination, what would happen?
Yeah, will the next step know if the previous step has failed or succeeded or not?
So this is so my best guess as to what would happen is it would probably say, okay, unable to, because there's a lot of things going on here. It's actually failing to figure out the route. It's actually needing to figure out a routing that will get them to the patient. And it actually uses a minimal distance routing, Dijkstra's algorithm, if you folks have ever seen that, and 280, maybe it is. And so it'll route them from A to B via a certain set of paths that have the least distance associated with the quickest way. And so if there ain't any path from A to B, if there's no way to get there from here, then I think it would say basically that in rather terse terms.
It would basically come down to the simulation would fail.
Yeah, I admire once again the Clintonian method, and I would advocate that breaking things or changing things is one of the best ways to understand what's really going on. So suppose we were to do that. Suppose we were to sever this very connection that unites this area here, which is where the staff, and then this. Yeah, but this is the operative path here that's shown here. So if we were to go in there, perhaps we'll do it for main phase 1, which is even simpler in its articulation. If we were to go in there, and we were to attempt to sever this, and again, this is getting us to the sort of latter logical half of the lecture, but I admire ambition, and will encourage this here. So I'm clicking down here. Okay, so we're going down. Did I skip polyline? This polyline 4. That's the one that kind of unites it all here. And so suppose we were to sever this so that, for example, it never twain shall meet. It can't go to this waiting room, right? Okay? Then the question is, what would happen? So now they can't get routed here. They can only get routed to this exit. They can't get here from this path. This is delineating the path by which they travel. And now I've routed them around so that it actually doesn't intersect with this path. It was routing them just like that over here before, and now we can't. So what do you think will happen? No, it will compile. It can't statically. It won't be able to determine this. That this is a problem. It's not going to run the algorithm to route them at compile time. That's a runtime operation, and so we can go and we can say, okay, run this with main phase 1. It's a simulation you can pick, and then I'll say, okay, go run. Boom. Okay, let's watch what happens. It compiles happily, and I'll start running this now. Let us await the first patient. Okay. Okay. Here we go. Hey. Oh man. There's no. Oh, there we go. See, network destination exit is unreachable from node procrum. So it. Yeah, it crashes. It says like can't get there from here. Sorry. There's a problem. But that helps us kind of understand where some of the logic is going on and what might lead to its failure. Now I'm going to restore this broken path. So pardon me for okay. Should be doing it up in main phase 1. Sorry. Okay, so I'm going to pardon me while I repair this thing here. Come on. Oh no. Yes, okay, there we go. Drag it back so that the vertex is located in this little box there, and this will allow it to be routed around, okay? Okay, great question. Okay, network attach. It actually attaches them to the resources so that they'll accompany each other henceforth, okay? Network move to. Now we're actually moving the entity to a resource. To what resource are we moving it? We're moving it to the proc room, okay? Now wait a minute, which proc room is this? Remember these operators were written from an entity perspective. So to which proc room do you think they're moving? The proc room that is associated with, it's reserved for them. It's reserved for the entity which is at this point in the progression. Okay. Now note, because we did the attachment, the entity moving there, guess who else comes along with it? The doctrine scope, because those have been attached to that entity. So they come along. They come along with that entity. Because those are the attached resources. Again, this is what I'm saying about this is an entity-focused description. Those sort of resources come along with the entity, okay? Okay, then we have a procedure, and that's particularly simple. There's just some delay associated with it. And then we have progressive undoing of this. We have a network detach. This detaches all resources from the entity. And then what has to happen next? Based on us running the model earlier. What has to happen next? So we release, or network detach, excuse me. This is not the same as release. Network detach, it detaches the need for them to travel together, right? They're still reserved for it. So, what needs to be done still? What still remains to be done? the scope has to go back to its home and the doctor has to go back. And can the scope go back to its home all on its own? No, it has to be carried. Guess who's going to carry it? The doctor. So the doctor returns to some specified node, the storage room, with the scope. And then, having returned the scope, those individuals or those resources can then be released from their reservation. Okay, so return the scope here, and following that, they can be released. And guess who still has to go home? Or go? Sorry, the doctor still has to go back to their home because they're at the scope room. Just got the scope there. Now we're saying release. We're actually de-reserving these things, so they're no longer bound to the patient. And guess what? For moving resources, they return to their home location, but it's releasing all seized resources. So it's releasing the proc room, it's releasing the scope, and it's releasing the doctor. And the doctor is going to go back to their home location. Okay? And then finally, we move the entity. This is a move to. So we move the entity to the exit, and they exit the network associated with it. Is that clear kind of how that works? So it's a little bit asymmetric in the sense we have these kind of entities and resources, and their entities have this kind of privileged existence in the sense that they're the focus of these operators, and these resources, some of them are moving in an agency, but they're kind of existing to kind of serve this entity. And these operators are written from the perspective of the entity. But it works. I mean, it works as a general strategy. So we have these set of operators, and what I'd say is actually an impressive achievement is the fact that AnyLogic, like many other discrete event modeling frameworks, you can have very large articulated series of flowcharts which describe quite complex situations, basically in a declarative fashion. When I say declarative, I mean we're specifying what is required in each of these steps. We're not writing a lot of code that actually does it. We're able to just say, okay, do this, do that, and it figures out the how. And it's actually quite declarative and frankly, fairly intuitive what goes on once you learn to think in that sort of way. You can kind of piece up, you want to describe a situation, you can kind of piece it up out of these pieces that, again, are specifying what needs to happen, so that you're not spending your time doing software engineering so much as understanding the basic flow of the process in the way that it frames it. Okay? So this is an example of flow. Now, any questions about the logic behind this before I go into the whole visual representation of that? I'm going to explore that a bit more, having given it a nod earlier. Yes.
For the network attached there, it says all seized non-static resources.
Yeah.
Is that, it doesn't seize the program because it hasn't moved?
Well,
Is that what it's
so
there?
it actually did. It's a great question. So the question concerned this network attach, where it says attach all, attach which? Well, attach all seized non-static resources at entity location. The reservation, the actual seizing occurred earlier. So the proc room is reserved along with the dock and the scope much earlier. This attach is specifically for the purpose of moving them with the entity. So when the entity moves, they will move with it, right? And so it makes sense that we attach to, in this sense, that they're going to move with us. They kind of bind to us for the purposes of movement. It makes sense that we're attaching to non-static resources. In other words, not fixed location resources like proc. Because there wouldn't be a lot of sense to say, you are chained to this room and you try to move, you can't move now. So it's only saying attach in the sense that they'll move with you these resources that are not fixed. It's almost by definition the only ones that can move are non-static resources. Does that make sense? Yeah. And as far as the static one, as far as the fixed one, in other words, the prop room, that's still reserved for you, and you'll be moving to it in due time. Does that make sense?
Yeah.
Good. Other questions? Other questions? I actually posted something to the Moodle site. It's a little challenge that challenges you to modify this model in a couple of ways. Okay? For those who are kind of interested in this sort of modeling, you're welcome to undertake that challenge. It can be quite a bit of fun, actually, to kind of try modifying these things. But to address that challenge, to confront that challenge, you'll want to understand some of the things that I'll be imparting for you in the next 20 minutes. Okay? Okay. So I would like now, in the absence of further questions about the logic, I would like to turn to the second component of this, and I apologize for the incorrect date there. So we're going to be talking about the visual representation of this now. So we've seen a logical flow of resources, a logical flow of entities through these flow diagrams. And yet, much of our first exposure to this model came by watching an actual animation of the model's operation. So if I were to run this here, I will go and run it. We'll notice that AnyLogic affords us a quite detailed visual representation of what's going on. Somehow all of this is choreographed in conjunction, all of the movement on the left is choreographed in conjunction with this flow on the right-hand side. And my goal over the next 15 minutes or so is to help you understand how those two come together. Okay. So let us begin. So we're going to see how those fit together. So the basic picture here, ladies and gentlemen, is that that entities and resources, and indeed, entities and resources and movement paths will be associated with visual depictions. So entities are associated with icons here. Resources are associated with icons that represent them, differential whether they're busy or simply waiting. In other words, are they currently being reserved? Have they been reserved? Are they seized? And resources are associated with locations. They have home places that they go. Give me an example of home places for any of the resources we've seen.
Storage space?
Yeah, storage space for the scope. Right? And for the staff, there's a staff lounge of sorts where they wait. So they have certain home locations. Okay. And then there's movement networks, which are associated with routing paths that we actually frobbed a little bit just a few minutes ago. And these allow AnyLogic to route entities and resources between different locations in an intelligent fashion. Okay. We move the doctor to the scope room, or we move the patient to the procedure room, or what have you. Okay. We can associate networks, the network as a whole, linking together resources, being associated with certain fragments of the flow, is further associated with a visual representation. You'll notice here, associated with this network down here, it says, hey, that's associated with the network group, which is actually a presentation group over here on the left. Okay, This differs from an AnyLogic 7. I'm showing you AnyLogic 6's depiction here. And you'll notice that this network group, if we go and we dive down over here, you'll see it's an embedded object. It's a presentation within here, and it has all these different pieces. A thing called waiting hall, a thing called staff room, a thing called storage room. Proc room 1, proc room 2, these procedure rooms, the exit. These are all marked. And you'll notice there's some further details specified. For example, when an entity is in a node, or a resource is at a node, such as a staff member, if they're in a node, say a staff waiting room, or a waiting room for patient, a staff lounge, they're drawn at a random location, or we can choose to draw them at the top left. Okay, so there's some bit of flexibility. So by virtue of associating with a network group, it kind of knows about these names. The waiting hall, for example, it knows what that means, or the staff room, because they have names within this group. Okay. Now the entity themselves, you can specify their depiction up here at the source. So in the source, we can specify there's an entity animation shape called shape patient. And by specifying different values for that, we could give them different visual depictions. So we can add in icons that represent people, and by changing that, we could change their visual depiction. Now, for resources such as doctors, we can specify, and I noted en passant that doctors are can be associated with different representations visually when they're busy and when they're reserved and when they're not reserved. And so you'll notice it says idle versus busy unit animation shape. So they're associated with representations that are different, and they're associated with a home location that's delineated. So let's perhaps to inject a measure of understanding, but also of levity here, we can associate doctors here with a different type of representation. Perhaps when they are busy, instead of representing them as a shaped doctor, we'll associate them with a depiction of a fighter jet, and we can copy them. And for certain doctors, orthopods are famous for being a bit overbearing. Perhaps this would be a nod, and it would not be unappreciated by the doctors. So here, doctors are waiting here. They're awaiting patient contact, but when they become busy, they quickly get rendered in an aviatory fashion, and they serve patients in this fashion. And then when they're done, they change back into a kind of standard depiction. So you see how the visual representations can be specified. And it affords us a certain flexibility. Okay, when people enter the network, we can specify where they enter, and we can further specify for the entities who are entering this network what their speed is, which would afford us an opportunity to change their speed, the assumptions about the speed of an entity, assumptions of the speed of a resource, we can also specify separately. Okay. Now the movement in AnyLogic 6, it's particularly simple. There's a whole space markup functionality that's been greatly enriched associated with AnyLogic 7. But AnyLogic 6, we have these so-called polylines, which we frogged earlier, which are routed among different components of the screen here. And you'll notice that these polylines intersect with these rectangles that delineate spaces, okay? So this network group, in addition to including some description of the scope and the patient and the doctor, it also indicates the set of these rectangles that are named resources. and these routing paths between them. So this is defined in this network group over here, and these routing paths use these polylines, and they allow the system to kind of know how to go from A to B. Okay. There's also some capacity to kind of say, hey, the procrums, for example, are defined by this path across nodes. So the procrums are defined, I think it's where the vertices are in this polyline. So there's one here at the end, one at the middle where it is crooked, and one at the end here. Those are landed on top of these rectangles, and they indicate that the rectangles are in fact the spaces associated with this resource. Okay, so it says home is defined by this polyline, which is shown here in red, room's location. Okay, so that describes the locations, the rectangles touched by the vertices. Okay, the exit node is defined in a certain location. Can't remember if it's, I guess it's this one here. And that allows us to move entities to particular points, like say go to the exit when they're leaving. Okay, so that's good. I would note, although I didn't comment on it in the slides, that that these resources, such as doctors, in addition to entities being associated with speeds, the doctors are associated with speeds, and in line with them being represented as fighter jets, we gave them a very large speed here, but we could change their speed and reduce the contribution of the afterburners, and we would see them move at a more stately pace. So this would lead to more patients accumulating in the meantime. Okay. So I've just given you a whirlwind tour of where some of the features of this model are defined visually, and again, much of it has to do with these various components here. We define for these different elements a set of visual resources, things like this. And I'm going to now remove the aviatory modifications. Okay. So any questions about what I've just shown there? So that's how the sort of visual representation is shown. Now, let me ask this though. I hark to a dichotomy between on the one hand the logical function of the model and the visual function of the model. Are those two solitudes? Are they truly in isolation from one another? Does the visual depiction we've just seen at all impact the logical functioning of the model? I put that question to you. Anyone?
I hope not.
Does it? Let me perhaps stimulate this with a further question. So over here we have paths depicted in this diagram. You'll notice that one of them is particularly circuitous. Do you think that would affect patient flow? Do you think that would affect how many patients we could see per hour?
I think so, but I think those edges are part of the logic rather than part of the...
Okay. Okay, no, fair enough. And if you want to sort of draw a different boundary there, that's quite true, Dustin's point, that maybe you argue that that's part of the logic. But you'll notice that these paths that they're going on are extra long here. And the point here is that the timing, that often these models are used, and a very high priority with these models is to understand the efficiency of the system, how quickly you can see patients. to try to avoid the very situation, ladies and gentlemen, seen before us, where we have an overcrowded waiting room, patients who are awaiting care, and we have, we're unable to keep up with it, and the patient flow in exceeds our ability to service them in an efficient fashion. Within that context, I would argue that the visual movement paths actually have a measure of gravity associated with them. So this circuitous path that bedevils this, that leads them to kind of go off in a tangent there, does actually have material implications for the movement. So I'm going to try to correct for that here. Trying to figure out it's this polyline 3. I'm going to move it down here and make it a more parsimonious route, and I will then go run this model, and you'll find that actually things do move more quickly. Whether it's quickly enough to keep up with this, given the slow speed I've put onto doctors, I would question, but it does allow a more efficient movement. So the point is that in this sort of modeling, the visual layout and the visual routing associated with things, the placement of resources such as proc rooms or staff lounges and so on, does have a very significant potential bearing on quantities, outcomes of great interest, to wit, things like patient throughput, how quickly we can see people, how many people per hour we can see, or the average time until we reach some capacity limit, such as just what we've just seen here. So one of the powers of this sort of modeling is that with only a very modest, this is not IQV, with only a very modest amount of changes, we could examine the impact in terms of how quickly we can service people come in, of changing, for example, of having a 4th procedure row. We could examine the impact of moving the scopes so that they and the doctors are located closer to the waiting room. We could examine the impact of shifting the geometry around so that, for example, the scopes and the doctors are more centrally located. These are things we could do. Could we do that in agent-based modeling? We could by programming it up. I mean, it would take quite a bit of effort to kind of do that. And the point is that's almost available for free with this sort of modeling. It affords us a really crisp way to kind of describe these layouts, describe the routing, and it takes care of a lot of things that if we were to have to do it, it would occupy at least a fair fraction of our time, writing the routing algorithms and reasoning about the shortest path associated with them, and the whole reservation of a doctor for a patient and the scope. We could do that in agent-based modeling, right? And again, it would be at an individual level, but it would require a fair bit of extra mechanism. It would require a fair bit of code. It would require a fair bit of extra work. Here, in discrete event modeling, these things are in the name of the game. They're easy to describe. We can characterize them with flow processes quite readily. We could see visual depictions of them, and more importantly, more deeply yet, we can capture the impact of these geometric considerations of how we reserve people, how we reserve proc rooms based on when someone comes in versus when a doctor arrives for them, and all sorts of things like that. We can easily change sort of our ways of doing things in terms of the patient flow, or in terms of how resources are allocated or what have you, and easily see the consequences. Could we do it in these other frameworks? Could we do it in agent-based modeling? Yes, but it would require quite a bit of extra work. By the same token, I would submit that if we tried to create an arbitrary agent-based model within this discrete event modeling, we would also be on somewhat of a fool's errand. In fact, we would have even greater difficulty trying to represent in this sort of framework, infection spread in a nosocomial context, in the context of a facility. It would not be amenable. There's not even an operator, I believe, in here to ask, for example, how many people are located close to me within a model like this. How many other people are located? You could ask maybe how many are in your same stage of the process, but how many are located within the waiting room? I don't think there's a way to ask that directly. And then in terms of sort of getting the proximity to others and the networks and so on, it would not be easy to do. And so this sort of modeling gives us a vocabulary, ladies and gentlemen, a set of nouns and a set of verbs. Entities, resources, nouns, verbs, much of them described via the flowcharts, to sort of characterize these processes of process-centric view of these entities flowing through these successive processes, operated upon through the use of resources, which, when unavailable, require queuing. That is sort of the hallmark of this approach, and it's a very concise and quite transparent way of characterizing situations where those things are to the fore. We will see this sort of modeling again, but not next lecture. We're going to continue on to topics like calibration, sensitivity analysis, dealing with stochastics, that encompass all three of these techniques. But we will return to this sort of modeling again, perhaps with a measure of fondness, when we examine hybrid modeling. And we'll see how this can be hybridized, particularly with agent-based modeling, to yield a very powerful combination indeed. Okay, so those are all my comments for today. I thank you for your time. I have posted a little exercise for those who wish to learn more about this sort of modeling, which could be good. If you'd like to undertake it, it's on the Moodle site. I note that the assignment is due shortly. I've been responding to quite a few questions, and I did post an updated version of the assignment with some extra comments and highlighted in red, which hopefully will speed you on your deliberations. And again, I will be accommodating as to this whole dysfunction, computational dysfunction, inability to log in, and so on. I'll be glad to allow for late-handeds as required to resolve those issues. Okay. So let me know if you are being troubled by those, and I have no problem granting extensions for that. Okay. But see, otherwise, if you can hand it in by Saturday. If any of you need, I've had a lot of one-on-one meetings with students. If any of you need to meet further with me, I'm glad to do it. Just let me know. Thanks very much. Can I ask you a question? Sure.